Hi everyone. In this video we're going to be continuing the robot color sorter series. We're going to be now adding the robot and the gripper as well as adjusting some robot properties in order to make it able to move efficiently without any errors to the cubes and the boxes. So the first thing we're going to do, we're going to click on robots. We're going to pick a non-mobile industrial robot. We can choose any, but the one I usually go with is the UR5 or 3 or 10, depending on the size of my setup. For this purpose, we're going to go with the UR5. And now we need to add the gripper. So we're going to Components, Grippers, and I usually go with the 3-finger gripper because it has a better hold, this one. And now we're going to be attaching the gripper to the robot. So the way to do that is we first open the robot hierarchy and we click on connection. So connection is this bit of the robot where we can connect the gripper to. And in order for the gripper to be connected to this connection, we need to drag it and make it a child of the connection. Currently it's not been moved yet, but now at least they move together. So now if I run the robot, we will find that the gripper also moves along with the robot as if it's attached to it, to the connection. In order to actually move it, first we need to stop the simulation. Then we click on the gripper and on move. On position, with respect to the parent frame, we need to set all these positions to 0. So now it's there. Now we need to rotate it. So we click on the rotation, orientation, parent frame, and we click on 0 here. So now it has the proper rotation. It just needs a few adjustments in terms of its position. We're going to click back on the position, but this time on the mouse translation with respect to its own frame. First we are going to, so we're going to undo that. Okay, we're going to first drag it along the Z, and we're going to be dragging it slowly, so we're going to change the translation step size to something a bit smaller. And we're going to position it there. And now we need to, so it seems fine in this direction, but here it also needs moving sideways. So we click on along Y and we move it sideways to center it properly. Okay. So let's move a little bit to, so this looks all right. Now if we run the robot again, we can see that the gripper is moving with it. The movement that you can see now with the robot is the default script that's present here in the robot, and the gripper also has a little window that we can use to open and close the gripper, just as an experiment. We can also do this action using the script, but this is just to look at it. And we can also change the finger angles. Eventually we want something a bit like this in order to hold the cube securely. There are two main ways to move a robot. The first one is kinematics and the second one is inverse kinematics. In kinematics, we start by specifying the joint angles, and then the robot moves and we obtain the position, which are based on the joint angles that we've specified. However, in inverse kinematics, we start from having a goal position, let's say the cube, and from that we calculate the joint angles required to achieve that position, and then we set the robot to have these joint angle values. So in this default script that comes with the UR5, it works using kinematics. So what does that mean? The first thing that happens is that in the coroutine main, this is where the main code is performed for the actions of the robot. This is, for example, just another function that is used from the main code. So This is the actuation. So this is the function that is going to continuously run throughout the simulation, and this is the initialization. And I believe this is just another function that is used as part of the main code. The first thing that happens is that we need to obtain the object handles for each joint using this function sim.getObject. And then here is where we specify the name of the object that we want to get, which is just joint, joint, joint. They're all called joints. And once we obtain those, what happens here is that the velocity, acceleration, and jerk values are specified. But actually we need to specify them as a vector because each joint could have a different value. Even if they're the same, we need to specify them as a vector of 7, I believe, 7 joints. 1, 2, 3, 4, 5, 6, or 6 joints. So a vector of 6 components. And then here we specify the target position, and in this vector we have the value of each angle that the joint needs to reach, basically. So for example, for joint 1 we need an angle of 90 degrees, which is pi over 2. So they're all converted to radian using math.pi over 180. And then we use the function move to configuration. We specify the joint angles, the maximum velocities, maximum accelerations, maximum jerk, and the target positions. And then the robot moves to these target positions. Now for the inverse kinematics version of the code, it's advisable to always start learning about code of CoppeliaSim from examples. So these examples, you can find them if you go into the CoppeliaSim downloaded folder and then click on contents, resources, scenes. Contents, resources, scenes. So this is where you can find examples about anything, including messaging, path planning, different demonstrations. So what we're going to do is we're going to click on kinematics, and we're going to open the inverse kinematics path generation one. As you can see, there's even more examples. For example, inverse kinematics of 144, a degree of freedom manipulator. So this is what we're interested in. So this example pops up. If we run it, we can see that the purpose of this example is for the robot to move from point A to point B, predetermined. So we click on the script of the robot, and just with a quick skim, so it has the same main components of a script, such as the initialization, the actuation, and then the coroutine main. So we always start reading from the coroutine main. The same thing happens. First, we need to obtain all the object handles of the joints, but this time also of the base, of the tip, and of the goal. So what's the tip? The tip is the object tip. So if we have a dig for it, it's a dummy that's attached to the end of the robot over here. The goal pose is another dummy specifying the goal position of the robot. So the robot needs to move from wherever it is to the goal pose. So the first step now for us to transfer this inverse kinematics code from this example to our own, simulation is we need to create the tip and the goal pose in our own simulation. In order to do that, we first go to the simulation, we click on add dummy, and now we've got a dummy here. We're going to rename it to tip, and we are going to attach it to the link 7 visible. Or actually, because we've got a gripper, we need to attach it to the connection point in the gripper. So this attach point in the gripper. So we're going to attach it to the attach point, make it a child of the attach point. Now, similarly to what happened before, when we add an object to another object, so when this becomes the child of attach point, The position of tip does not necessarily change, but they do become attached to each other. But in order to change the position, we need to click on position, position parent frame, and we set everything here to 0. And similarly, we go to the orientation and we set everything to 0 just to maintain the same orientation. So now we've got the tip over here. Now we need to create another dummy, which is the goal position. This dummy, we don't need to make it a child of anything. It can be independent in the hierarchy. We're going to call it goal pose, the same as what we had in the example. And that's it. And now what we're going to do is we're going to go back to the example. We're going to copy all this code and we're going to paste it over here in this. Now if we click on run, we can notice sometimes nothing happens. So this is because the goal pose is probably in a position that the robot cannot reach. So what we need to do is we need to move the goal pose to a position that the robot can reach. So I'm just stopping the simulation. We click on move, we select the goal pose, and we move it around to another position. Let's try this one. And now we can click run. So now we notice that the robot is going to the position, back and forth. We can also adjust the constraints of the inverse kinematics in this command. Add inverse kinematic element from scene. At the end of this command, there's an option called constraint position. Position means the XYZ of the goal pose. So if it's constraint position, that means that the tip is going to have the same XYZ position of the goal pose. If I say, for example, orientation, that means only the orientations need to match. So let's try saying orientation, see if anything happens. So now they are matching in orientation only, not necessarily in position. The goal pose is in a completely different position. The robot is just trying to match its orientation. If we say pose, that means both orientation and position. So instead of this, I will say constraint pose. And now if we run it, we notice that the robot did not move, which means that the position plus orientation together are not attainable for the robot. Let's try moving the dummy again. So trying different positions, still not working. Maybe we can vary the height. Not working. So we'll have to do more adjustments and adjust the constraints as well, and maybe the tolerances, and make this work hopefully. In the next episode, we are going to be obtaining the goal pose from MATLAB, because eventually the goal pose will have to be the cube position itself. So we're going to be sending the cube position from MATLAB to CoppeliaSim and then moving the goal pose automatically to overlap the cube so that the robot can eventually go to the cube position in order to pick it up. Thank you for watching, and if you have any comments, please leave them in the comments below. Thank you.